What did we do last week? We've seen the definition of randomized computing. Okay, how do we formalize that? How do we evaluate randomized algorithm? Okay, and we've seen two examples of problems where randomized algorithm perform well. One was for the min cut, okay, where we could get an efficient and simpler algorithm, okay, by using randomness. And another example was the counters. So where we saw that counting up to n on expectation can be done using only log n bits of memory with randomness. Okay. So in this session, we will continue studying some random algorithm for problems where randomness helps a lot. Okay. So what I plan to do is to have basically 3 examples in these lectures. So the first 2 ones will be of the same kind, where you show that randomness helps a lot, okay? And the third one, we will start another chapter where we will see how randomized algorithm can help analyzing deterministic algorithm, okay? So on trivial examples, but anyway, that's the spirit of it, okay? So today what we will see is first, the evaluation of boolean trees, okay, and second, the optimization of the energy consumed by an hard drive. Okay, and so on this one we will have a better time, and here we will have a better saving. Okay, so here what we had is that it was simpler, and here what we had, it used less memory. Okay, so better saving, that is to say better cost. Okay, so we will have more or less a complete pictures of all the objective function we may dream of, and see for all these objective functions that randomness can help. Okay, so by the way, do randomized algorithms do always better than deterministic ones? Absolutely, I mean, does the best randomized algorithm do better than the best deterministic algorithm?
You can always use a randomized algorithm ignoring randomness to make it easier.
Okay, any deterministic algorithm is just a randomized algorithm that ignores the random bits. Okay, so randomized algorithm can always do better, okay? The optimum one. Okay, good. So let's see the evaluation of Boolean trees. So let me know if you already know this example, okay, because it's quite common. So the whole, it comes from game theory. Well, no. If you look at the best randomized algorithm, it's always better than the best deterministic one. So the problem is maybe you will not be able to come up with it. But
the question is if you look at true random algorithms.
Well, well, why would you look at something like that? I don't know. If the best randomized one is deterministic, then you should consider the deterministic one. You should not consider the randomized one. Yeah, sure. But you know, you can have a deterministic answer but a random time. Also, it's still randomized algorithm. Well, yes, in this example here, we will see that randomized algorithms do truly better than any deterministic one. So it will be an example for you. Okay? And in fact, in those two examples here, we will get the best randomized algorithm and show that it's strictly better than any deterministic one. Okay. So it comes from game theory. So what's the spirit of that? Is basically you want to design a winning strategy. So a winning strategy, what is it? It's a strategy where whatever the adversary plays, you can always play something so that you will end up winning. Okay? At any step, whatever the adversary may try, he will always lose. Okay? So you're looking for such a strategy. So how do you model that? So basically what you want is that whatever the other one does, you will win. Okay? But what the adversary will try is to win. Okay? So basically what do you want is that for whatever choice I make, okay, there exists no. Whatever choice the adversary make, there exists a choice. Oh, that's the opposite, sorry. So what I want is that when it is my turn, there exists a choice for me such that whatever the adversary make, there exists a choice for me such that whatever the adversary makes, and there exists a choice such that I win. Okay? This is basically what you want to solve. Okay? There always exists a choice for me, such that whatever the adversary makes, there exists a choice for me, such that whatever the adversary makes, there exists a choice so that I win. Okay? So basically, what do you want? Imagine that 1 is I win, and 0 is I lose. Okay? And imagine that at any step, there are only two possibilities. Okay, so we will see an example of such a game afterwards. So what do you want? You want that there exists a choice for me. Okay, so basically what do you want is, imagine that you will build a tree here, and the result of this tree here will be 1 if I win, if this chain is okay, and 0 if not. Okay? So what do you want is, you want that in some of this tree evaluates to 1. Okay? You will be able to win if some of this tree evaluates to 1. Okay? So basically, what you have at the root of the tree is a OR. Okay? And now what's on the next level? So here it's I play. And on the second level is the adversary play. The adversary plays. So what does he want? He wants to win. Okay? He wants to win. So what does he want? He wants that basically, none of these three allow me to find a path to win. Okay? So what's going on? The only way I can win here for sure is only if both of these three evaluates to 1. Okay? If one of these three evaluates to 0, then the adversary will choose this path, and he knows that there is one way to force me not to win. Okay? So basically, what does he want? He wants that if there is 1 0 here, there will be a 0 there. Okay? So basically, what are these nodes? These are n nodes. Okay? So basically, what do you have here? You have at the beginning, you have a tree of alternating AND or OR gates. So here it's a OR, and then AND, etc. Okay? And at the end, you will have leaves where it's 1 if I win, and 0 if I lose. Okay, at the end is that. Yep.
It's not so clear because they have two leaves connected that may win me and the adversary.
No, in the leaves, it's the final configuration of the game, okay, and one has win, and there is no tie. We imagine that there is no tie.
There is no, but suppose two leaves with the same parent make me win or the other.
So, what I mean is that at the end, everybody has played, the game is terminated, and one has win, the other has lost.
Yes, but suppose I
So if there are two win here,
one win and one loss.
one win and one lose, okay? So if it's the adversary turn, then it's an end, and the value is 0. There is no winning strategy for me.
Okay.
You got it? Okay, so an example would be, for instance, so this is, do you get the picture here? So basically, what do you want? You want that OR it's the same as there exists, and AND is the same as for all. Okay, so there exists a choice for me, such that for all choices of the adversary, I will win. Okay, so evaluating those three will just gives you whether there exists a winning strategy for me or not. Okay, so what is an example of such a game? Such a game is simply you take the exact same tree. So you take a binary tree here. Okay. Okay, and etc. And at the end, you have 1s and 0. Okay, it's just so you have a token here at the beginning, and you choose to move it to the right or to the left. Okay, and then it's the adversary to move it to the left or to the right. And if you manage to move the token up to a 1, you win. If the token ends up on a 0, the adversary wins. Okay, it's exactly this game. Okay, so just one after the other, you will move the token here. So for instance, let's consider the following tree. Oops. Too many of them. Okay. So let's look at this tree here. Okay, and you have 1 and 0 here. 1, 1, 0, 0, 1, 0, 1. Okay, so you have this tree here. And basically, the token is here at the beginning. So I will try to move it there. I don't know, the adversary will move it here. I will move it here. And then the adversary move it here. He wins. Okay? So now the question is whether there exists a winning strategy for me or not. So what I will just evaluate the nodes. So here it's the AND end level, here it's an OR level, here it's an end level, here it's a OR level. So what I will do, I will just so I will compute the value. Here the value is 1 because it's the end of 2, 1. So if I manage to force the adversary to get there, then I win. Okay. Here the value, the end is 0. Here the end is 0. Here the end is 0. 1, 0, 1, 0. Okay. So now I do the OR here. It's 1. Here I do the OR of these two things. It's 0. The OR here is 1, 1. Now I take the end of this is 0. The end of there is 1, and the OR is 1. Okay? So there is a winning strategy for me here, which consists in doing this move here. Then the adversary, whatever his choice is, will lose. For instance, imagine that the adversary goes there. Then now I know that there is a winning strategy for me, which is moving there, and whatever choice the adversary does, he ends up putting the token on a 1, and he loses. Okay? So if I was to move there, you see that the adversary can move there, and then I'm lost. Because whatever I do, I will not be able to find a winning strategy. Okay? So the question now is, given a Boolean tree like that, okay? So given that the tree has n leaves, what's the size of the tree?
I mean, in the general case, I suppose not all passes terminate in the same depth.
Yes, we end up all at the same depth. Okay, so else it gets messy. I mean really messy. There is no theorem. So as far as I know. So if your tree has n leaves, what's the size of the total input? Everything. Okay, so you have a log n depth. Okay, and how many nodes do you have? What? 2n. Yes. Okay, it's 2n. You have 2n nodes. Okay, so basically the size of the input is big O of n.
But the input is in fact only the...
Yes, only the leaves. Yeah. Only the leaves is okay. Okay? Good. So what we want to evaluate this tree in time f of n, where n is the number of nodes. Okay? So how long does it take to evaluate it deterministically? What, please? So 2 of n? No, there is n leaves. Okay, so there is n leaves. So let's say that the depth is k. Okay, in fact it's 2k. It's 2k because you have r, or, and end. Okay? So you have depth 2k. So now how long does it take to evaluate this tree deterministically?
The total number of nodes is
2n, yes.
So it takes 1.
2n, yeah. It's big O of n. Okay? So deterministically, it takes big O of n steps. Can we do better deterministically? Why?
We have at least to read all the leaves. So
Why?
because if we just flip one, we don't read, we can just change everything.
How do you prove that?
I would put, I don't know, or gate maybe, and show that flipping one bit can change everything.
Yes. How would you do that?
We can find a configuration where just flipping one bit at the end just change the issue of the game.
Okay. So the whole spirit would be yes. It's not possible. That means it's theta of n, exactly.